Let's talk about a force. A force so powerful it can light up our world or bring it to an end. It's hidden deep inside the heart of every single atom. We're talking about radioactivity, the atom's own double-edged sword.
You know, it sounds like something straight out of science fiction, but it's not. It's happening right now all around us, inside everything. At the very core of every atom, there's this epic, invisible struggle going on, a battle that literally decides if the world around us holds together.
So who are the fighters in this atomic showdown? Well, on one side, you've got the repulsion force. Just imagine trying to shove the positive ends of two strong magnets together. They push apart, right? That's exactly what protons are doing. But holding them all together in this impossibly tight grip is the nuclear binding force. It's this unbelievably strong power that just overcomes all that pushing. It's like a constant cosmic arm wrestle.
But what happens when that cosmic arm wrestle gets, well, unbalanced? What happens when one side starts to lose its grip? That's when things get interesting. The atom's core becomes unstable, and that's when we see the phenomenon we call radioactivity.
So how does that balance get tipped? Well, in some atoms, the mix of neutrons and protons just isn't right. There's too much energy packed inside. The nucleus gets kind of heavy, bloated, and really unstable. The binding force just can't hold it all together anymore, and the atom has to do something drastic to fix itself.
To get that balance back, the unstable atom just decays, all on its own. It starts shedding all that excess energy and matter, releasing it out into the world as radiation. This isn't something we make it do. It's a completely natural process. It's just the atom's way of finally chilling out.
And that energy it's shedding, it's not just some random burst. Nope, it's released as specific types of invisible radiation. The main ones you hear about are alpha particles, beta particles, and gamma rays. A good way to think of them is like tiny bullets being fired off by that unstable atom, all in its quest for a little peace and quiet.
Okay, so once scientists figured out this was happening naturally, you know what the very next question was, right? Could we control it? Could we trigger that incredible release of energy whenever we want it? And that one question, right there, led humanity to a massive fork in the road. Path number one is the controlled reaction. This is the whole basis for nuclear power. Inside a nuclear reactor, we kickstart and very carefully manage a chain reaction. The whole process generates a truly insane amount of heat. And from there, it's pretty simple. That heat boils water, the water creates high-pressure steam, and that steam spins a turbine to generate electricity for all of us. And the ways we can use this controlled power are, well, they're pretty mind-blowing. We're not just talking about huge amounts of clean energy. In medicine, we use radiation to find and fight cancer. In farming, it gets rid of pests. It helps make the silicon chips in your phone, and it even powers rockets that explore deep space. The potential for good here is just enormous.
But there's the other path, the uncontrolled reaction. This is what happens when you let that chain reaction just run wild. You don't manage it, you let it cascade. In less than the blink of an eye, the energy release goes exponential, and the result is a massive, devastating explosion. This, right here, is the dark side, the principle behind an atomic bomb.
Which leads us to the absolutely terrifying reality of what happens when that control is lost by accident. And the most infamous example, the one we all think of, is the Chernobyl disaster. It's the ultimate story of a controlled system spiraling into an uncontrolled nightmare. So, back on April 26, 1986, a safety test, of all things, went horribly wrong. It caused a catastrophic power surge. The reactor core completely melted down, and then a massive explosion just ripped the whole building apart. A huge plume of radioactive material was blasted high into the atmosphere. It wasn't a bomb, but that radioactive cloud didn't care about borders. It just drifted wherever the wind took it, contaminating huge parts of Europe. And here's the really insidious part. The danger was far from over after the explosion. That fallout was full of dangerous radioactive stuff like iodine and cesium. This invisible poison rained down, settled into the soil, got absorbed by plants, which were then eaten by animals, and eventually it made its way right into the human food chain. A silent, invisible, long-term threat.
You know, the legacy of disasters like Chernobyl really forces us to ask some hard questions. How do we actually live with this kind of technology? How do we measure the risk and protect ourselves from a danger we can't even see? When it comes to the health effects, it really all depends on the dose and for how long you're exposed.
getting hit with a large dose in a short time, that's called acute exposure, and it does immediate and severe damage. But then there's chronic exposure, getting small doses over a long period of time. That's dangerous in a different way, leading to a higher risk of cancer and even genetic damage.
To manage all this, scientists came up with strict safety limits. They measure radiation doses in a unit called a millisievert. For the general public, you and me, the annual limit is just 1 millisievert. It's incredibly low. Now, for trained radiation workers who have all the protective gear and protocols, that limit is higher at 20 millisieverts. But even that is watched like a hawk.
So really, it all boils down to two key strategies: protection and prevention. For protection, workers have to wear specialized suits, gloves, and masks. And for prevention, well, that's all about the nuclear waste. You can't just throw this stuff away. It has to be sealed in layers of cement and rock and then buried deep, deep underground in places that are geologically stable, far away from any water, volcanoes, or earthquake zones.
Which brings us back to the ultimate question. This incredible power locked inside the atom. It's given us clean energy, life-saving medicine, and a way to explore the cosmos. But it's also given us weapons of unimaginable destruction and the potential for accidents that can scar the planet for centuries. So what do you think? Is it our greatest tool or our biggest threat? Maybe the answer isn't really about the atom at all, but about us and how we choose to use that power.